Thank you for the invitation. So, I would like to discuss some rather recent work, but well, not recent, at the same time very old and very recent work related to some invariants of Euclidean lattices that turn out to fit very nicely with many other aspects of Arakelov geometry, and to give some new understanding of some very classical result in Diophantine geometry that can be understood as some kind of algebraization statements. So the key notion I would like to explain in this series of talk is the notion of infinite rank Hermitian vector bundles. So as you probably know, or as you will know very soon in this summer school, Hermitian vector bundles, so to speak, are the basic objects that are studied in Arakelov geometry. And to summarize things very quickly, infinite rank Hermitian vector bundles play the same role with respect to Hermitian vector bundles as Hilbert spaces play with respect to finite dimensional Euclidean spaces. So that's the kind of generalization that is quite natural in analysis, of course, that turn out also to enter naturally in Diophantine geometry. Okay, so in this series of lectures, I would like first to give some general outline and then to go back in more details on some points. So today I would like to explain a few very basic facts concerning Euclidean lattices seen from the perspective of arithmetic geometry, of Arakelov geometry. And then I would like to introduce the main character of this series of lectures, the Theta invariants of Euclidean lattices. I would like to explain why the Theta invariants, in some way, even if you are interested a priori in classical Arakelov geometry, in some sense, you can't escape this definition involving Theta invariants. It will be the third part. I will also discuss a little bit with some more details the situations where one deals not with a vector bundle over spec Z, that is Euclidean lattices, but when one works over general arithmetic curve, namely spectrum of the ring of integers of a number field. And then I will turn to the heart of the matter, the infinite rank Euclidean lattices and their applications. Okay. So let me remind you a few classical facts concerning Euclidean lattices. Okay. So Euclidean lattices are very easy to define. Maybe I should say that these notes are available on the web site. They have been posted by Emmanuel. Okay. So a Euclidean lattice is given by a finitely generated free abelian group, E. So that's Z at some power n, and some Euclidean norm on the underlying real vector space you get from E by extending scalars from Z to R. So of course, it's basically, once you have chosen a basis of E that identifies E with Z at the nth power, it's nothing but the Euclidean norm on Rn. Okay, so it's really, you think of this data is, you have this underlying real vector space, and inside this real vector space you have a lattice, a subgroup generated by element of a R basis of ER, And besides, you have some Euclidean norm. Okay, so Euclidean lattices have many interesting invariants. The most trivial one is the rank, the dimension on the underlying vector space of the rank of the Z module. Okay, Euclidean lattices have a very long and very rich history. The case n equal 2 is known in some sense for centuries, not centuries, but okay, maybe tens of centuries. It's related with tilings and weaving. As far as I understood, lattices in the case n equal 2 really appear in the mathematical literature in the work of Lagrange in relation with the study of quadratic forms in two variables. And in a way, Euclidean lattices in dimension 3 have been considered by mathematicians earlier than in dimension 2 because of crystallography. And actually, as far as I know, in modern science, they appear in the very famous book of Huygens about the theory of likes, where there is a Huygens principle at the end of the 17th century. And here is the oldest picture of a mathematical Euclidean lattice I have been able to locate in the literature. Of course, I had a discussion on this topic with Gerhard von der Heer. And the position of Gerhard von der Heer is that it's extremely likely that Hellenistic mathematicians are on Archimedes and had ideas about Euclidean lattices in dimension 3 in the modern sense. But it has been destroyed at some point. Okay, so the theory of crystals led to some classification of lattices. And people like Gauss were, of course, very much interested in it, and Bravais. And then in the 19th century, Euclidean lattices of arbitrary dimension have been investigated, and basically in relation with arithmetic, starting with the work of Hermite, and with the so-called geometry of numbers, and which was also mainly developed by Minkovski in very geometric terms. And some very deep work that is, in a way, not completely well understood, have been developed by people like Voronoi and Delaunay at the end of the 19th and beginning of the 20th century. Okay, so the point about Euclidean lattices is that these mathematical objects are very easy to define, but they lead very, very quickly to very difficult questions. So, for instance, you may consider the space of isomorphism classes of Euclidean lattices. So if you go back to the previous definition, you have to, once you are given a Z basis of the Euclidean lattice, it is given by some Euclidean metric. The space of Euclidean metric is GLNR divided by ONR. And this, by elaborating on this discussion, you get that the space of Euclidean lattices is this space of double classes, GLNR divided by ON divided by GLN. And this space, actually, is a very interesting space when n is large. Okay, that's the space where automorphic forms lives. So basically, the analysis on the spaces is supposed to encode all, or at least a large part, of Diophantine geometry, if you believe in the Lagrange program. When the n becomes large, the topology of the spaces can be quite complicated in a sense, especially if you're interested in distortion coefficients, because it encodes the K-theory. And from a different perspective, it's known now that you can construct public key encryption systems that use lattices of large rank as basic objects. Okay. Okay, so that's a fact of life that they are easy to define but difficult to describe. So let me go back to some very, very elementary facts concerning Euclidean lattices. After the rank, which is very, very stupid invariant, so to speak, the next invariant of a Euclidean lattice is its covolume. So if you start from a Euclidean lattice, you may consider its covolume. It's a positive real number, which is the Lebesgue measure of a fundamental domain of the lattice. So on the underlying real vector space of the lattice here, you are given a Euclidean norm. So you have a naturally associated Lebesgue measure, a translation invariant measure that gives the volume 1 to the cube of size 1. Okay, it's well defined. On besides, you are given the lattice, the n inside here, and you may consider a fundamental domain. So here is may be written as a disjoint union of translate, let's say, of Borel subsets. And it's very easy to check that the volume of this fundamental domain doesn't depend on any choice. And this is the covolume. Okay. So from the point of view of crystallography, the covolume is something quite natural. The inverse of the covolume is the number of lattice points per unit volume. If we have a Euclidean lattice that is a model of some big crystal, of some substance, the inverse of the covolume, so to speak, is the density of the substance. Now, it's very easy to see that the covolume of the direct sum of two Euclidean lattices is the product of the covolumes. So there is an obvious notion of direct sum of Euclidean lattices. You have the direct sum of Euclidean of vector spaces. You have the direct sum of Euclidean vector spaces. You have the direct sum of lattices of Z modules, and they fit together, and you get an obvious definition. So it's some kind of product. And the very definition, the fact that the Lebesgue measure of a product is a product of the Lebesgue measure, translates into this multiplicativity of the covolume. And actually, this multiplicativity plays a central role in oracular geometry, a very basic role. And it's nicer to work with some additive version of this multiplicativity. And actually, the so-called Arakelov degree of the Euclidean lattice E bar is minus log of this covolume. So you take the log to get something additive from this multiplicative relation. And you have a minus because you want to have a lattice with very small fundamental domain to have very large degree. Okay, so I did rewrite the multiplicativity as this additivity relation. Okay, now very stupid remark, which is something which will play a role over and over. It's the properties of this invariance under scaling. So if you start with some Euclidean lattice E bar, you may rescale the metric by multiplying by any positive real number. And actually, it's natural to consider the group action of R defined by this scaling. So it's natural to multiply by exponential minus t. And you may think of this as some kind of twist by some kind of line bundle. Okay, so it's straightforward that when you rescale in this way, you multiply the covolume by exponential minus t times the rank. So when you take the Arakelov degree, this scaling operation add to the Arakelov degree the terms t times the rank. It's additive. Okay, all this is very simple, but okay. Now, to put in perspective the role of this theta invariance that I want to discuss in these lectures, I need to remind you a few basic facts, elementary, classical facts concerning short vectors in Euclidean lattices. And all these reasonings will involve some computations of volumes. So it's very important to keep in mind the asymptotic behavior of the volume of balls in the n-dimensional Euclidean space when n goes to infinity. So let me explain this. So let Vn denote the Lebesgue measure of the n-dimensional unit ball. So there is a closed formula for Vn that you get very simply by computing the integral of a Gaussian function. Well, you can also prove it by induction, but so the point it is basically pi. Well, it's pi at the. It becomes very, very small. It's something like factorial of n over 2, inverse. Okay. So the asymptotic behavior is obvious by Stirling's formula. Log of x factorial is x log x minus x plus a little of x. So this shows that the Vn at the power 1 over n is equivalent to some constant times 1 over square root of n. So you see, so this means that in dimension n, if you want to have a ball, well, the radius of a ball of volume 1 is approximately square root of n. And based on this factor square root of n enters in many estimates, in many relations, in Arakelov geometry. So if you, in a very heuristic way, you may understand it in the following way. If you live in some non-Archimedean world, there is no difference between cubes and spheres. But in the real Euclidean world, there is a difference between cubes and spheres. And the penalty you have to pay in dimension n by unit, by dimension, because of this reality of the world is square root of n. Or, of course, if you take the logarithm, if you are interested in the Arakelov degree, you will have to consider logarithm. So you see log of Vn is divided by n is something like minus 1/2 of log n. Okay. Actually, if you don't like analytic computations, you may observe that the ball, Euclidean ball of radius 1, contains these cubes of size 2 over square root of n by Pythagoras formula. So you see that Vn is at least 2 over square root of n at the nth power. So you say this very naive inclusion gives you the right order of size of this Vn at the 1 over n. And of course, it gives you these estimates on the log of Vn. So what I just discussed before, you don't need to do some complicated computations. It's really, at least the right order of size comes from this very naive estimate. Okay, now let me turn to Minkovski theorem. Okay, if you are given a Euclidean lattice, okay, you may define many invariants, of course. And so the first one is a rank, second naive one is a covolume. But you may also consider the length of the shortest non-zero vector. So this is traditionally denoted lambda 1 of E bar. So it's the minimum of the discrete set of lengths of these non-zero vectors. And now, okay, so in crystallography, it's something that has a very clear meaning. It's the closest distance between two different molecules in your big crystal. Okay, now if around every point of the Euclidean lattice, you consider the ball of radius 1/2 of the shortest distance, by construction, all these balls are pairwise disjoint. I suppose it's clear. And if it is not clear, this is a picture by Huygens of this proof. Okay, Huygens has really the drawing is exactly what I said. He has represented a ball around each point of the lattice of diameter this lambda 1. So they just touch them. Okay. Okay, so these balls are pairwise disjoint. Consequently, the density of your lattice is at most the inverse of the volume of these balls. It's clear. Okay, so if you write this in formula, it means that the inverse of the covolume is at most Vn lambda 1 over 2 at the end, the volume of these balls, inverse. And this estimate is known as Minkovski theorem. Okay? It gives you an upper bound for lambda 1 in terms of the covolume of E bar at the power 1 over n. So, of course, in a way, the fact that you have a power 1 over n is clear for dimensional reasons. And the maybe mathematically the non-trivial factor is this factor that involve the volumes. Okay, so this is Minkovski theorem. And so, of course, you have this estimate. Vn at the power minus 1 over n is something like square root of n. So this is a very easy estimate. So it gives you the fact that lambda 1 of E bar is at most square root of n times this covolume at the power 1 over n. Actually, the best possible constant in any given dimension n in this inequality is traditionally called, or rather its square, is called the Hermitian constant. So it is a number that is known for only a very, very short family of values of n. It's really vexing that one is not able to prove this. So the previous reasoning shows that the Hermitian constant is at most n. And actually, it's known since Minkovski by, Minkovski, some application of the Ziegel, Minkovski-Ziegel integration formula, that this estimate is basically optimal up to some constant factor. And if you prefer to, in hierarchical of geometry, one prefers to work with logarithmic invariant. So this estimate takes this form. Minus n log of lambda 1 is at least minus n over 2 log n plus hierarchical of degree. So you are in dimension n, and you work here with volumes invariants like hierarchical of degree. For every dimension, you have to pay a penalty of 1/2 of log n. So at the end, you have n over 2 log n in the estimate. Okay. So this is very classical, but as you will see, it's important for the sequel. Okay, now I would like to say a few words concerning the analogy between number field and function fields and the perspective it gives to geometry of numbers and works on lattices. So it's a very, very long story. In a sense, it starts with the work of Dedekind and Weber who wanted to provide some purely algebraic foundation to the work of Riemann on algebraic curves. So they really developed the theory of, let's say, purely algebraic theory of algebraic curves over C. So they wanted to develop the notion of also, let's say, Dedekind ring, so to speak. First in the geometric situation over C, and then in more general setting. And Kronecker also played a very important role with some competition with Dedekind and Weber to the fact that working in a way schemes of finite type over Z are important, and you have, okay, if you consider an integral scheme of finite type over Z, it can be flat over Z, it's an arithmetic case, or it can be a scheme over some finite field, the purely arithmetic situation. So it was really Kronecker that understood that. And Kronecker had a student, Hensel, who invented a lot of things motivated by this perspective, including the periodic numbers, and who understood the fact that Archimedean places had to be put on the same footing as finite places. And of course, German school, around Artin and Hasse, really elaborated on this. And more recently, of course, Weil was largely motivated by this perspective. The Russian school, around Shafarevich too. And this led us to Arakelov, so now I don't add any name because you will learn a lot of things about that this week. Okay, so I would like to focus on the most basic aspect of this analogy. And I've drawn some picture here. Okay. So, in the analogy between number fields and function fields, you have number fields, so you have facts about number fields, so you see you have a lot of holes. And you have function fields. So function fields, there is this old paper of Weil that explains that it's better to have two columns for function fields, the columns where the base field is FQ and the one where it is C. But for a reason of size, I have put only one column. Okay, so number fields are fields like Q, or finite extensions of Q. And since the work of Dedekind, one work with the integers, the ring of integers, so it's easy if you start with Q, or you take the integral closure of Z in K in the general case. In the function field case, you start with a small base field. So in real life, well, for all these people, the case of FQ or C plays a very special role. Then, what plays the role of Q is a field of rational function, K of T, in one variable, whose coefficients lies in this very small field. And the ring of integers is, K is replaced by this polynomial ring. So that's another basic example of the Dedekind ring. And now, of course, as in the number field case, one work also with finite degree extension, the same for function fields. So when we work with field of rational functions over a smooth projective curve over the small field K. So in the green case, where the base field is C, this field of rational function is really what was considered at the beginning of the story by Riemann. It's a field of meromorphic function on a compact connected Riemann surface. Okay. Now, when you study Riemann surfaces, of course, vector bundles, analytic vector bundles, notably analytic line bundles, play a crucial role. If you work with the tangent bundles, the differential line bundles associated to divisors. And it turns out that in the world of number fields, Euclidean lattices are analog of vector bundles. Now, if you have a vector bundle, it has a degree. In the complex case, the vector bundle of a compact Riemann surface is a topological vector bundle that has a degree. So a class in H2, C1 has a class in H2. Of course, you may give a more algebraic definition by asking the degree of a vector bundle to be the same as the degree of its determinant, of its maximal exterior power. And now you are reduced to defining the degree of a line bundle. A line bundle is always defined by some divisor. It's O of sigma of Ni pi. And you may define the degree. So in the complex case, it will be the sum of the Ni's. If you work over a field that is not algebraically closed, you have to take care of the residual degree of the closed point pi. It's given by this formula. And actually, in the world of number fields, the Arakelov degree of Euclidean lattice is really the counterpart of this. Okay. Now, if you are in the function field case, of course, since Riemann on Rohr, on F.K. Schmidt, one has proven some form of the Riemann-Rohr formula. The Riemann-Rohr formula gives you some information about the space, which is a finite dimensional space, vector space over the small base field of section of a vector bundle E over the curve C. So you may consider the space of section on its dimension. So its so this dimension is a non-negative integer. And the Riemann-Rohr formula tells you that, okay, h0 minus h0 of the third dual is given in terms of the degree plus correction depending on the rank of the genus. Okay, now what I would like to explain is that in the number field case, of course, there are holes in this column. Well, there is no clear or completely definitive, of course, it's not completely clear what small k is. It's not completely clear what should be the counterpart in this column of this space of section. But it turns out that in the classical literature, there are two counterparts to these numbers. There is this, what is considered by, I don't know, Arakelov and all other people, already they, some H0 Arakelov, and there is another kind of invariant which has been introduced by the German school that I will denote H0 theta. And these invariants are real numbers. It has the point of Arakelov geometry, intersection numbers that replace in the arithmetic world intersection number of algebraic geometry that are z-valued. This, okay, arithmetic intersection numbers are r-valued. And here, these numbers that play the role of dimension are non-negative, so they belong to R+. Okay. So now I would like to explain what this object is, and later on I will explain how it extends to some kind of infinite dimensional objects. Okay. So let me introduce first some kind of classical counterpart in the arithmetic world of this dimension of space of sections. Okay, start with any Euclidean lattice. And you may consider the number of lattice points in the unit ball. You may count these points. And you may take the, work logarithmically, take the logarithm. And this by definition, it is this H0 Arakelov of E bar. So, a few comments. This number is of a point in the unit ball. It's always at least 1, because you have always 0. So the logarithm is always non-negative. Okay. For something supposed to be a dimension is not too bad. Okay. Actually, this definition is implicit in some classical, very old paper of André Weil precisely about the analogy between number fields and function fields. It's also, if you look at the article of Arakelov at Vancouver's ICM, where it introduces, where he explains basic facts concerning intersection numbers on arithmetic surfaces and attached invariants. This definition also appears there. So I suppose it was very well known by people like Shafarevich and Parshin. So I tried to find some precise references. It's explicit in some work on some paper of Spiro on Manin in '85, and it has been much discussed in some very nice short paper by Gillet, Mazur and Soule in '91. Okay. Oh. Okay, maybe a short, an important observation that is, of course, already in all these authors, starting with Weil and Arakelov, is that you see, asserting that this H0 Arakelov is positive is the same thing as telling that lambda 1 is at most 1. You need to have a non-zero vector of the lattice in the unit ball. And Minkovski theorems tell you precisely that as soon as the degree is large enough, it's true. So something similar, of course, holds over a function field. If the right-hand side of the Riemann-Roch formula is positive, the dimension of space of the section is positive. But here you see you have this, the rank appears linearly in the function field case. Here you have this bad logarithmic factor. You have log of rank k. Okay. Now let me turn to the other invariant, H0 theta. So that is the main character of this series of lectures. So here is the main definition. H0 theta is the logarithm of this theta series Okay. So of course, it's clear that if you have a lot of short vectors, it will be large because the Gaussian decrease. Okay, a few comments. So here again, it's non-negative because you always have 1 in the sum. The sum is at least 1. Actually, it's always strictly positive if you are not in rank 0. Okay, it's a very, very old definition. Actually, if you compare the proof by Hecker of the functional equation for the zeta function of a number field and the later proof in the function field case for a function field, so in one variable with a finite base field that is due to Schmidt, FK Schmidt, you may compare the formula. And you see that what plays a role of in echoes to space of section, or what is explicitly a dimension of a space of sections in F-K-Schmidt is that kind of number. And actually, this was certainly well known by the German school. Clearly, Artin was absolutely familiar with this. And if you look at the Tagebuch, the mathematical diary of Hasse, there is an entry in February 34 where he gives he summarizes some explanation of Artin about this, that explains this. And there is also some trace of this in Tate's thesis. As you know, Tate was an Artin student. Okay. And actually, these invariants have been considered again more recently from the perspective of Arakelov geometry by van der Heer and Schroff in a paper published in 2000. And a PhD student of them, Groenewegen, did also obtain very nice results. And a few months ago, I did post on arXiv some paper on which this series of lectures is based. But actually, this definition appears more or less explicitly in various guises in other places. For instance, you may consult Quillen's mathematical diary on some website in Oxford. It has been numerized by the Clay Foundation, and it is extremely interesting. And actually, this is explicitly discussed in 71, 73, and 83. And also, Damien Rössler did write some Diplomarbeit related to that, at least in the line bundle case, in 93. So you see, it's something, really in the air for a long time. Of the trivial one. Yes. Oh, that's something. Okay, I did not want to discuss, but you can. And actually, if you take the basic Euclidean lattice, there is a closed formula, and actually it's a number which has been computed by people like Abel and Gauss, because it's really related with some lemniscatic period. There is a formula in terms of gamma. And actually, you can prove, it's a nice exercise. You start with some integral lattice. If you use a little bit of class field theory, you may prove that it is always of the form, the rank times this lemniscatic basic case, plus the log of some real algebraic number related to some class field. So it's a fact that for lattices that are on some arithmetic meaning, integral lattices, these numbers are very remarkable by class field theory. But that's something I cannot. That is very deep in a way. But I am unable to relate to the other aspects I want to develop in these lectures. So that's something quite interesting in itself.
So is there any non-arithmetic lattice in the Euclidean space?
Now, by arithmetic, I mean you see in a lattices defined by you want the square of the Euclidean norm to take integral values on the lattice points. So it's defined by if you start with a Euclidean with some quadratic form, it's a quadratic form with integral coefficients. Okay, so maybe I should discuss some of the very basic properties of this invariant. So it's important to understand the precise normalization. Why is it pi or not pi over 2 or 2 pi? Or, okay. So this is a very simple question. The point is that it corresponds to the fact that the Gaussian integral, well, in any dimension, if ER is a Euclidean vector space of any dimension, you may consider the Gaussian function exponential minus pi, the square of the Euclidean norm, and you may integrate it with respect to the natural Lebesgue measure normalized by the in terms of the Euclidean norm, and it is 1. Okay, it's a basic Gaussian integral. So you see, it is the same. Okay, and here, of course, if you have to put pi there to have this formula. And it is the same pi, so to speak. So for instance, from this formula, you get this one. You may compute this integral as the limit of Riemann sums. You may discretize by replacing the sum, the integral, by the sum over lattice points, and you may shrink the lattice by multiplying vectors by epsilon. And of course, you will have some factor like 1 over the unit, the fundamental domain, and of this shrink lattice. So it gives you this formula if you go to infinity. All right? And this formula, from the point of view of algebraic geometry, is quite a nice formula because you can rewrite it logarithmically. You take the logarithm, and it means that, okay, if you write epsilon, what is the writing? I suppose it's epsilon is octet inverse. It tells you that if you take this theta invariant of this scaled lattice, oh, there is no log there. It's a mistake. If you take the theta invariant of the scaled lattice, you twist the lattice by this scaling factor, when it goes to infinity, it behaves exactly like the Hilbert polynomial of a vector bundle on a curve. You have a linear terms in T, which is the rank. You have a constant term that is the degree. And then you have a rest that goes to 0. And actually, you may very easily check that the rest goes very, very fast to 0. In the geometric case, this formula becomes, the same formula is true, but it relates integral numbers. So when T is large enough, the rest is 0. So you may think of this formula as something that tells you that the H0 theta is related to the Rykilov degree in the same way as the dimension of space of section is related to the degree given by the Hilbert polynomial. So you have to erase the log. Okay. Okay. Another very nice property is that H0 theta satisfies some counterpart of the Riemann-Roch formula. So you have to remind you what is a dual Euclidean lattice, which will play the role of a dual vector space. So if you are given a Euclidean lattice, you have a dual lattice that you define by taking the dual Z module. And actually, if you take you have some obvious base change. E dual, base change to R identifies to a lattice in ER dual. And of course, you also have a dual norm, but that is a dual norm in the sense of the theory of norm vector spaces. But of course, it's a Euclidean norm too, which is defined by the, if you think of the Euclidean norm as an isomorphism between the whole vector space and its dual, it corresponds to the transpose inverse isomorphism. So this is a very basic definition, which is completely clear from the point of view of hierarchical of geometry. If you have Hermitian vector bundles, you have basic tensor operations like tensor product, exterior powers on dual that make sense for Hermitian vector bundles. And this is the simplest case where you consider Hermitian vector bundles over spec Z. But it is also something that makes sense in physics. It's quite important in physics, in crystallography, when one does X-ray crystallography. Well, what one observes is a dual Euclidean lattice of a lattice. So this is a very interesting. There is a very interesting story about that because it was discovered by von Laue, and von Laue had some discussion with Ewald, who was working theoretically on the propagation of waves in lattices, and by Piosok realized that the formula, the mathematical formula, would say that one should be able to do crystallography, well, X-ray interferometry, and analyze the structure of crystals in this way by using short wavelengths. Okay, and actually the mathematics that is besides the X-ray crystallography is a relation between lattices and Fourier transforms on the Poisson formula. So let me explain this very shortly. If you are given a Euclidean vector space, you may consider the Fourier transform that transforms, let's say, Schwartz functions on the Euclidean vector space to Schwartz functions on the dual Euclidean vector space. And you may also work with tempered distributions. Okay, so for instance, the Fourier transform of functions with rapid decay may be defined by this formula. I will use this normalization. So actually, you see here, you don't really need the whole structure of a Euclidean space. What is important is basically the Lebesgue measure. Exactly something that plays a role, that will make sense with a real vector space plus the choice of a Lebesgue measure. Okay, so this definition, this red definition makes sense for any functions with rapid decay or for L1 function, but actually extends to tempered distributions. And a specific tempered distribution associated to a lattice is a sum of the direct measure at the point of the lattice. So there's a counting measure on the lattice points. And the Poisson formula tells you precisely that the Fourier transform of this discrete measure, which gives the weight 1 to each lattice point, is the Fourier transform, is a discrete measure on the dual lattice up to some normalizing factor, which is the covolume. So that's something you prove very easily by basically it corresponds to the following manipulation. You start with some function phi on E, for instance, with the infinity with compact support on the Schwartz class. From this function, you get a infinity function on the quotient of ER by the lattice by adding the translates by all the lattice points. And now, this is it's a compact torus. You may consider the Fourier transform of any function there. The character of this compact torus is related with the dual lattice. And if you express the Fourier inversion formula for Fourier series for this function, you get this formula. Okay? That's something very basic. And actually, you may apply this Poisson formula to a Gaussian function. So if you want, you may take the scalar product, you may evaluate on a Gaussian function. And then it tells you that you take this Gaussian sum on the dual lattice. It is equal to the Gaussian sum on the initial lattice up to some factor, which is the covolume. To do that, you need to know, you have to know what the Fourier transform of a Gaussian is. But you know, of course. On this formula, okay, it's a Fourier, okay, it's variation of the, you may, if you rescale it, it gives you some functional equation for the theta function. So it's a very old formula that goes back to Poisson and Jacobi. And now, if you take the logarithm of this relation, you will get the H0 theta invariant of the dual lattice there. There you will get the H0 theta of E, and this will be to assign the Arakelov degree of E bar. So you have this formula, you take the logarithm, and you get the fact that H0 theta of E minus H0 theta of E bar dual is the Arakelov degree. And you see, this formula is really, looks really like the Poisson, the Riemann-Roch formula for a vector bundle over a compact Riemann surface of genus 1, where you have no, the factor 1 minus g disappears. And this, of course, was well known, I suppose, to people like Artin and Hasse. I suppose it's also one of them. Yes, the canonical is in the situation when it is trivial, like the trivial case, like for an elliptic curve. So, of course, you get, for instance, from this that H0 theta is at least the degree. So this formula is somewhat similar to the one we have before with, as a consequence of Minkovski, if the degree is large, H0 theta has to be large. But you see, you have no nasty constant. And that's really the point of all the story, is that the rank of E bar does not appear in these relations. While it always appears, you cannot avoid them. You can prove you cannot avoid that kind of, if you work with similar, well, if you establish similar relation with the more naive H0 Arakelov invariant that counts points. And actually, this is a very general philosophy. And in a sense, even if you are at the end ultimately interested in H0R, my feeling is it's always better to do all computation with H0 theta and only at the very end to go back to H0R. So I would like to discuss a few aspect of this philosophy that is very satisfying for the point of view of the analogy. It means that for the point of view of the analogy with with confunction fields, that H0 theta invariants are much better behaved. Of course, there is also something I should emphasize, which very strangely was not has been proved only very recently, is that the H0 theta invariant is not really different from the H0R. So I would like to discuss this a little bit. For instance, the H0 theta invariant of a direct sum is a sum of the H0 theta. And it's basically clear. If you take this theta series for a direct sums, you will get something the norm of VW is and of course this is a product of the theta series for E on the set of series for F, and you take the logarithm, you get this addition formula. This is completely elementary. And this is not true for if you count naively the points. Another property that is indeed quite remarkable is that you have some subadditivity. If you have a short exact sequence, an admissible short exact sequence, I will explain what it means in 1 second, of Euclidean lattices over spec Z, you may consider the 3 invariant H0 theta, and you have this inequality. So this inequality is an inequality that is trivially satisfied if you have 3 vector bundles in a short exact sequence over a projective curve, because then you may consider the long exact sequence. You have you really have an exact sequence of space of sections that are finite dimensional. And of course, the exactness of the sequence implies a similar inequality for the dimensions. And here, it's the same inequality holds, not for integral valued dimensions, but for this real positive real invariance. Okay, so this subadditivity is some nice exercise you can do. It has been observed by Quillen. Actually, I was very proud to observe this, and then I realized that it was been observed by many, many years ago by Quillen in his notebook. And actually, it's a consequence of Poisson's formula for general functions of the positivity of the Fourier transform of the Gaussian. So it's not very difficult, but really it really directly relies on Poisson's formula, on the fact that a Gaussian function is of positive type. Its Fourier transform is always non-negative. So I have to explain what this means admissible. So if you consider a diagram of Euclidean lattices, it means that is an admissible short exact sequence. So it means that you are given a short exact sequence of Z modules on purely algebraic notion. And moreover, you assume that the metrics are compatible, namely the injections from E to F comes from some injective isometry from ER to F, and that the norm on GR is a quotient of the norm on F. So this object really plays a role of short exact sequence for Hermitian vector bundles. So here is a picture. So you have the big F bar, you have E bar, which corresponds to this line, which passes injectively, and you may consider the quotient, like in this picture. Okay. Of course, in general, such an exact sequence is not split. It's not at all a direct sum. Okay.
Wait, sorry. In the previous picture, where does the admissibility fit?
In this picture? The admissibility means that here you see you have this F bar. So the E bar is really this sublattice with a given metric. And the G bar is the quotient. So it's the quotient in a purely algebraic way. It's also with quotient norm. So it corresponds to the fact you have to take the orthogonal projections to the orthogonal of this ER. Yes, it's like this, but you see, you have some freedom. It's not split because you can slide this way, and it gives you the same E on G bar, and the extension is different. And now the other point I wanted to emphasize is that the German invariant and the Russian invariant are not that different. There is a comparison estimate. In dimension n, their difference is bounded purely in terms of n. And you have two inequalities. The first inequality is very easy. And the second inequality is much more serious. But here you see again, you have a penalty of something like n over 2 times log n. the same kind of bad numbers that occur. And okay, C is some universal constant. 1 is okay. It's very small. And the lower bound is trivial. These bounds are basically optimal. You can prove this by this Ziegler's mean value formula. But the upper bound, in a sense, is not trivial at all. It's I did prove this by some variation of some very beautiful techniques introduced in the 90s by Banashik to prove certain estimates in geometry of numbers. And that's something I will explain later on. So the point of view of Banashik is that when you have given a Euclidean lattice, you may consider the discrete measure, which is supported by the point of the lattices, but where you give some Gaussian weight to the points. And Banashik introduced this measure and plays with the Fourier transforms, and it's a way to establish very deep results in geometry of numbers. And by the same techniques, you can prove that. Okay, I have still half an hour, no, 20 minutes. Okay. 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 Now, in a sense, the situation is at this point is somewhat puzzling because you have these two invariants of lattices. So traditionally in the literature, the Russian influence of Arakhelov has been maybe the strongest. So many results are given in terms of number of lattice points in the unit ball. But what I would like to explain is that if you take the Arakhelov definition, the counting points definition seriously, and you try to improve it, you can't escape the theta function definition. So that's something I would like to discuss now. So it's related to what you could call the thermodynamics of Euclidean lattices. Okay. Okay. First observation. All these invariants of lattices, if you deal with invariant of lattices, it's always natural to consider their behavior under scaling. You may scale the matrix. After all, there is no serious reason to consider points in the unit balls rather than points in the balls of, I don't know, size E or 2 or anything. So you may consider how it varies when you scale the metric. And let me define H0R E bar of T as the logarithm of the number of points in the ball of radius square root of T. Okay, why do I take the square root of T? Why do I consider this condition square norm smaller than T? Because it's almost straightforward that this number satisfies this condition. If you have a point in E1 whose square norm is at most T1, another in E2 whose square norm is at most T2, if you take together, they define a point in this direct sum of square norm at most T1 plus T2. So now if you count, you get, and take the logarithm, you get very easily this estimate. Okay. Another thing you can very easily check by some elementary volume argument is that if you replace E by n copies of E and T by n times T, as a function of n, this number grows linearly in n. And now, okay. The difficulty with H0R is that it behaves very badly, for instance, with respect to direct sum and so on. So a very naive idea is, okay, you start from this invariant H0R, and you try to improve it by some kind of limit argument. So once you have observed these two properties, there is some kind of obvious limit procedure, which is motivated by the classical lemma of Fekete, that tells you that if you have a sequence that is super additive, then the an over n has a limit, which is a sup. This is a basic estimate, for instance, that Fekete used in the theory of transfinite diameter. So this is very elementary thing. So, using the previous observation, you see that the Fekete lemma applies to this series. So you may take the limit. So it's some kind of smoothed version, stabilized version of H0R. Okay, something you really want if you want to have something which is more additive. For instance, this is additive with, maybe not in general, maybe not for E1 and E2, but if you in powers of E, by definition. That is not the case of the initial invariant. Okay. And now I claim that this new invariant actually is basically, up to some subtle twist, this invariant. So here is a theorem. If you start from a Euclidean lattice, you may consider two invariants, or rather two functions, because you allows to scaling. You have this H0 tilde E bar, so maybe I should write what it is. So you have this stabilized Arakelov invariant H0 tilde R, and you have the log of the theta function. So the theta function is actually the twisted version of H0 theta. Let me write what it is. So it's some H0 theta of some twist. Maybe I should not write T, but anyway. So I claim that you get two functions on R plus star, that both of them are very nice, real analytic, concave and convex respectively, and that actually they are related by Legendre duality, by convex duality. So it means that you can recover the H0 theta for log of theta, and conversely by this Legendre duality formula. So of course this implies directly many estimates when you evaluate this formula for some fixed value. But it means that, okay, from this theorem you may deduce many unicity statements about functions that look like H0R and that are additive and so on. But really, that's a result, it's a conceptual result at the heart of the matter. Okay. Okay, actually, in the literature, I finally realized that it was proof for the rank 1 trivial lattice in a long paper by Mazzo and Odlesko in 90. But actually, the difficulty I had to prove this is that basically it has nothing to do with Euclidean lattices. It's something that holds for very, very, very general reasons, related with the theory of large deviations of the thermodynamic formalism. And I would like to explain this shortly during the last 15 minutes. Maybe I should show you pictures. So you see, I try to draw some pictures. You have the function log of theta, which I write psi, this red function, and you have this h0 tilde function over there, this red function, and this is realistic. It's like they look like this for lattices. And this h0 tilde, here I write s, and you may recover from log of theta by this Legendre transform. You are given some, if you are given some x, you look at the line through the origin of slope x, and you look at the largest distance between this curve and this one. And in the other directions, it's similar construction. You are given the h0 tilde, you are given some beta, and you can recover, okay, the notation is slightly different, but you can recover this log of theta by taking this curve, this line of slope beta, and by looking at the maximal distance. So that's So let me explain this. It's directly related to the formalism of large deviations. So it's really funny that this plays a role in the theory of lattices. So let me consider the following data. Suppose you are given a space with a measure and with some positive function. So you are interested in physics, and you have a very naive model. It tells you that you have some phase space, which is this E. You have some measure mu on some kind of Borel set T in E. And moreover, you have some measurable function H, which corresponds to some Hamiltonian, to some energy. Okay, so this is a phase space that represents say one particle or very elementary system. Now, you may consider a large number n on copies of, well, on n copies of your systems. So mathematically, it's represented by E at the power n, equipped with the nth tensor power of the measure. And you define some kind of total energy of a multiple E1, En as a sum of their energy. And you may consider the measure of the volume in this big space representing n particles of the points where the total energy or the average energy of the point in the multiple is at most x. So that's something that enters naturally in probability. It was developed by Kramer, actually. So in that case, the total measure is 1. You describe a probability. H is a random variable. And this question of understanding the measure of the set of points where the sum of H1 plus Hn is at most n times x is something quite important for actuaries. It was developed by Kramer. Well, Kramer first did a thesis in number theory, and apparently he had problem with Mittag-Leffler, so it was difficult for him to have an academic career. So he went into mathematical finance, so to speak, and he used the same tool, and he developed the theory of large deviation. So you say you have a lot of, you have some assurance contract for some specific categories of people. On H is what the assurance company has to pay for the kind of average or standard accident. So you have a very large number n of people who buy the contracts, and the difficulty for the company is to know that, okay, what is the x, such that in general this is very large. Well, 1 minus epsilon. You want to be sure that even if you have a lot of difficult independent accidents the same year, you will not get bankrupt. So you have to understand that kind of number. But it also appears more or less explicitly in statistical physics. Then E is a phase space for some system. And in general, the total measure is infinite. Not always, but if you have a finite total measure, you will have negative temperature. That's something classical in physics, but rather funny. And H is, of course, the energy. And N, of course, is the number of elementary particles that compose the statistical system you are interested in. Okay, so let me rewrite the assumption. In this situation, it's important to introduce this kind of logarithmic Laplace transform of the function h. You take log of the integral of exponential minus beta h d mu. And you assume that the function h grows in such a way that this is finite. So this is a very mild consequence. It says that the, okay. You may consider the essential minimal of the function, the measure of the point where the h is the smallest possible. Okay. And now you may prove the following very general theorem in this setting. So that's something which mixes many things. That goes back to Kramer. Lanford, a mathematical physicist, did some significant progress on this. And you need to adapt, to add something. Okay. So the point is that the measure you are interested in this situation, if you look at this logarithm, for any x, it's super additive. And you may apply this Fekete trick and consider the limit, which will be something in R. So it means, in a sense, that kind of measure has some kind of exponential growth in n. And this S of x is a measure of the exponent. And it's easy to prove, that this function is increasing. And actually, it is concave. It's maybe not that easy. So the first part of the theorem. And this logarithmic Laplace transform, it's always real analytic and strictly concave. And actually, you may consider its derivative. It's negative, so up to a sign, you may consider the derivative, which is this expression, which is the classical expression for average energy at inverse temperature beta in statistical physics. And the point of the theorem is that in this setting, up to some sign, this function s that gives you the exponent in the growth of this, and s goes to infinity. So this kind of entropy, and this function psi is it's a Planck's thermodynamic functions. It's a variation of the free energy, are always Legendre transform of each other. You will always have these functions, these relations. This is already an instance of the relations we had to learn when we were kids, relating entropy and free energy. And something that is a corollary is that the S, which is given by this limit of 1 over this is at first sight, it's very difficult to understand the regularity of these functions as a function of x because of the limit exists pointwise because of this Fekete theorem. But because of this convexity property and this Legendre transform, as the function psi is real analytic, it implies that this function s also is real analytic. That is not trivial at all. And actually s as a derivative, that is the inverse of this energy function u. So it's really a situation, an instantiation of the thermodynamic formalism. Notation have been chosen to be evocative. Beta is the inverse of the temperature, u is the energy, s is the entropy, and f is the free energy. And now, okay, this is the picture that explains the relation between these functions. And you may apply this to a Euclidean lattice. If you have a Euclidean lattice, you may take as a space the point of the lattice, and you take as a measure the naive counting measure. And of course, the square of the Euclidean norm gives you some function h. And if you apply the very general formalism above to this situation, you get exactly the first theorem telling you that the log of this function and this function are Legendre transform of each other. From a physical point of view, what you are looking at is a statistical physics of a quantum. You are looking at some kind of hybrid statistical physics. You are looking at the classical statistical physics of a quantum particle on the dual torus. Okay. Voilà. The function psi is log of theta. Okay. On the entropy, so you are in the situation, if you want, the log of theta, the H0 theta invariant, is a kind of free energy of Planck's thermodynamic function, and the Arekelov type invariant is some kind of entropy. Okay. Okay, maybe I should conclude on the following thing. What is the counterpart for lattices of the second principle of thermodynamics? Here it is. If you take two lattices, you may consider the direct sum. The second principle tells you what happens when you have two systems, they are in contact and blah, blah, blah. You the heat goes in the right direction till they are to the same temperature. And here it translates in the following formula. The H0 Arekelov invariant of the direct sum is given by this definition, this formula from this H0 invariant of the two components, of the two factors. And actually, this formula, okay, you may say something more. And this formula is the Legendre rule of the additivity relation for log of theta. Okay. So I suppose, okay, it's really funny to have thermodynamics of lattices, but in a more pragmatic way, my feeling is that if you want to prove this formula, you can state with very, very few preliminary, it's basically necessary to have this theta invariance and to have these relations. So I gave this as an instance of this general philosophy that asserts that even if you are ultimately interested in classical invariants of lattices, like H0R, it's interesting to investigate closely the H0 theta invariance. Okay, thank you.